Hi, welcome to Intermolecular Forces, IMF, and Solubility. Please answer these questions before continuing on and have your responses ready when we come into class. So this is not part of your notes, but I found this actually afterwards. I thought would be good into determining if something is polar, meaning is a molecule polar. So if we follow this along, types of bonds. Nonpolar bonds, it's got to be a nonpolar molecule, no doubt. If it's got polar, you need to look at its geometry. Symmetrical means can you fold it in half and have things reflect and be the same on either side. Asymmetrical means you can't do that. When you fold it along an axis of bonding, it doesn't line up, so it's going to be polar. If it is symmetrical, terminal atoms, those are the atoms on the outer edge, the outside. If it's all the same element, it's going to be nonpolar. If there's some different elements, it's going to be polar. If you apply this polarity decision tree to many of the things we talked about before, you'll find that to be true in the VSEPR theory diagram or lecture. So to help you understand this decision tree, let's talk about these things individual. I made a goof that you want to change these terms from bond to molecule up at the top of each of these columns. So polarity depends upon two things: the polarity of the bonds and the shape of the molecule. We've talked about the polarity of the bonds a little bit and the shape of the molecule a little bit. Now we're just putting them together. So I put the examples of nonpolar, polar, and then again ionic bonds, not very useful for this, but it all comes in the same category. So in a nonpolar molecule, like I said on the decision tree, no positives and negatives in the structure. It may have polar bonds though, so they can cancel out, much like in the idea of carbon dioxide. And there is no negative or positive in the bond. So the idea is that you have no positives and negatives, much like you see here. That could be true for a nonpolar molecule. Polar molecules does have positives and negatives in the structure, has polar bonds, and the negative portion is assigned to the more electronegative atom of the bond. So these things are a little bit of review, a little bit of new. We're kind of mixing both. Let's take a look at shape. So there's some shapes that are always non-symmetrical or asymmetrical. Those would be bent and trigonal pyramidal. Okay, just those two, because there'll be an uneven balance of these charges here. Now, what are shown as the arrows with the pluses are what are called moments, the dipole moments particularly, and those are found and done for the bonds in these cases and can be done for the entire molecule. But I often think of these roles as being, is there a positive end and a negative end to the entire molecule? So take a look at just these figures that I have here. I'll use my black here. So between hydrogen and chlorine, which one is closer to fluorine? That would be chlorine. So it's going to be partially negative, making hydrogen partially positive. Is there a positive end and a negative end to the molecule? Yes, there is. So it will be polar. Over here, which one is closer to which one is closer to fluorine, nitrogen or hydrogen? Well, nitrogen definitely is, so that's partially negative, meaning each of these is partially positive. You might notice that the dipole moments, the arrows, have the back end of the arrow, not the sharp point, not the point, but the back end. I think that's called, not a quiver, fletch? I think it's called a fletch. Anyways, that looks like a positive symbol, so it's near the positive. Is there a positive and negative end to this molecule? Yes, there's a positive bottom portion and a negative top portion. When we look at this idea of here, chlorine is going to be the partially negative one when bonded to the carbon. However, with carbon and hydrogen, let's erase that. The hydrogen will be positive for each bond with the carbon. So there's 3 partial negatives when it comes to each of those positives. So this area up here is partially negative. This area down here is partially positive, therefore polar. When we think of nonpolar, look at each of these with boron and fluorine. Partially negative, partially negative, partially negative, and this one would be partially positive in the center. So is there an end, a tip of the molecule that is negative and one that's positive? No, it's not, so therefore it's nonpolar. Same holds true here. These are all partially negative when bonded to carbon. So this has a core of positive, while a perimeter, an outside area, a shell of negative on the outside. That's why it's nonpolar. So this evaluation of the shape and the individual bonds helps determine, is the molecule polar or nonpolar? And if it's symmetrical, that plays a role in it could be or it could not be polar. You have to evaluate them on a case-by-case basis. But you can do that. Now we've talked about solubility with things that were ionic in like water. However, things that are covalent work similarly but are slightly different. So when we think of things that are nonpolar, something like hexane is nonpolar, like you see in black, and water molecules you see on the bottom. So they're not likely to mix because of the fact that all the positives and negatives in here don't really have much to grip onto in these nonpolar hexane molecules. So hexane's less dense, so it's going to float, but there's nothing bringing them together. It'd be like trying to pick up a greased, block. If you can't get a good grip on it, how are you going to move it anywhere? So this idea that things that are both opposite charge or opposite polarity, nonpolar, and things that are polar are not likely to mix very much. However, nonpolar is a different story. So with the idea of nonpolar, if I were to say, would these mix? And let's say this is, what's another one? I don't know, C2H4, ethene. These would mix together because if they're both nonpolar, they're going to interact as if they were the same thing. And just like the hexane molecules in a jar of hexane, those molecules are going to be free to move all within the liquid anywhere. So because they are the same, they're going to freely mix back and forth, which is going to have them mix together. So nonpolar will dissolve with nonpolar. When we think about polar solvents, they are the same. So much likewise, all the hydrogen bonds between ethanol molecules and hydrogen bonds between water molecules, this makes them very polar. And because they're very polar, there's a lot of positives and negatives. Let me change colors here, positives and negatives. So all of these positives and negatives can grip each other, and where you get full mixing all throughout and very thorough interaction. So polar will dissolve polar because the positives can attract the negatives that are present, mix them very thoroughly. Nonpolar does this because essentially they have no polarity, so they're essentially the same, and because they're the same, then they're not going to separate from each other, they're going to easily mix with each other. Polar doesn't mix with nonpolar because there's nothing for gripping together and that there's difference in density, so they stay separated from each other. So let's take a look at these intermolecular forces that I've touched upon a little bit. So when you have polar molecules, those molecules have dipole-dipole forces. And all that means is that there's a positive and a negative in one molecule attracting a positive and a negative in another molecule. Sometimes they can be the same molecule, like water, or it could be something like water and ethanol, two different molecules, both being polar. Couple representations down at the bottom. You have the partial charges, which you've seen me draw, the bond dipoles, which is the same idea, just a different representation, and then what's called the net dipole. That would be the idea of the polarity of the molecule. We're not going to go through drawing those and all of that stuff, but I want to show it to you just in case you see it in other sources. So this electrostatic attraction is these dipole-dipole forces, which cluster them together when they would normally want to be far apart. Just like we see with a lot of these in this picture here, there's attractive forces and repelling forces. Of course, the positives are going to repel the positives and the negatives are going to repel the negatives. Likewise, positives attract negatives, as long as everything is close enough. So in something like this, you can see that there is some attractive force. It looks like there's a lot more green than there is gray. A lot more things pulling them together than pushing them apart. Like I've said this whole time, chemistry is all about positives attracting negatives. So this attractive force can have a pretty big impact on some of the properties that we see concerning these, as we'll see by the data of boiling points. So before we talk about what hydrogen bonding is, let's just take a look at the idea of polar. So, oxygen, O2, which is nonpolar, is about the same mass as HCl, which is polar. Look at the difference in their boiling points. Negative 183 to negative 85. Again, the lower negative, or I should say the higher negative number, meaning less attractive force, it can become a separate gas at a lower temperature. So just because it's polar, it has so much more attractive force to be a liquid 100 degrees Celsius higher, even though it's about the same mass. And mass does play a role. So that's huge. You also have the idea of H2S and H2O. That deals with the idea of hydrogen bonding. Hydrogen bonding is not a bond. It is an intermolecular force or an intermolecular attraction. Even though it has bonding in the term, it just isn't. Sorry. So hydrogen becomes strongly attracted to an electronegative atom like nitrogen, fluorine, or oxygen. When that occurs, that partial charge is really, really high, so that attractive force is going to be really, really high. Remember, if you increase the charge, you can increase the attractive force. So take a look at the difference with that with H2S and H2O. H2O has hydrogen bonding. H2S just has dipole-dipole. Even though sulfur is heavier, look at the huge disparity, 161 degrees difference in being a gas or a liquid between the two. Huge. Phosphorus has dipole forces, NH3 has hydrogen bonding. Again, you can see that it has a pretty remarkable difference, even though phosphorus is heavier. 55-degree difference. Pretty large. So hydrogen bonding is a much stronger attraction, not bond, attraction, than dipole-dipole. Has a big impact. Now we're going to stop at our last one, which are London dispersion forces or London forces or dispersion forces. This is the idea of nonpolar. So this is where a permanent dipole can what's called induce a dipole, to where if you have a nonpolar molecule on the right and something that is polar on the left, because this negative gets close, it's going to repel electrons. I don't want to do that. Say erase. It's going to have the electrons, which are always around, and it's going to push them away, repelling. When it does that, it makes this side partially negative because the electrons went away, which leaves this side partially positive. And in that moment, there's a slight attraction between the positive that's existing in the induced dipole and the negative of the permanent dipole. that attraction does have an impact and is the only one found between noble gases and nonpolar molecules. However, it is present in all molecules. This does get larger with increased atomic mass. So if we take a look at this, all of these are nonpolar up at the top, and we can see that H2, the lightest, has the lowest. Oxygen, higher. Chlorine, much heavier, higher. Bromine, right below chlorine, is still much higher. Even though these are all nonpolar, the increased mass, the number of electrons, means that there's going to be more of these partial induced dipoles, which is going to increase the attractive force. Look at the difference between CH4 and CCl4. CH4, nonpolar, CCl4, also nonpolar. Much heavier, huge difference in their attractive forces. Huge. So that makes a big difference in the idea of how these things attract. So again, all of these attractions mentioned are weak in comparison to bonds. If I were to list the forces in this chapter 6, all this about bonding, ionic would be the highest overall. Covalent would be second. We don't talk about metallic here. We used to, but it's not really that important. That would be things found in like alloys, that type of attractive force. But then you have your attractions down below. Hydrogen bonding, dipole-dipole, and then London. So keep those in mind as you're trying to explain what's going on, the difference between bonding and attractions, polar, nonpolar, covalent, and later ionic when we mix them back in. Come to me with any of your questions, and I'll talk to you soon.